And in this section, we go through the so-called government use cases, and there are 4 of those, and we will describe each of those 4. And these 4 will actually have quite a bit of description of the categories, because when a category first appears, we will describe it. We will not describe it when it appears later on. So you will find the earlier use cases have more discussion of categories than the later use cases. So here's our first use case, which is actually rather unusual, in that it's the census data from 2010 and 2000, whereby the law of the land, the data must be preserved, and you can access it, but only perform analytics after 75 years. And the data until then is stored as is, with no access to the public and no data analytics. The data has to be preserved in the totally precise fashion, accurate to the nearest bit, and if necessary, you're going to have to change formats, because at the very least, hard disks and will probably not be hard disks. Well, it will not be what's used 75 years from now to store data, and tapes will also disappear. So quite what they will be, whether it'll be a giant blancmange of biological material or some quantum pizzazz system in 75 years from now, we don't know. But the census has to do all those changes. And this is all done through Title 13 of the US Code of Law. And this current data is 380 terabytes. And here at the bottom, we have our first introduction to the categories. We will describe those on the next slide. MRStat is MapReduce for statistical analysis. SSQ is search and query. Index is indexing. And those are in blue because they're computational types. And in purple, we list the form of parallelism, because all of these things need to be parallelized. Here we have census data from every household. And so the parallelism is over households, or effectively people. So here is the slide, which will always look like this. I say they tend to be more complete in the earlier use cases, which actually use a particular idea for the first time. And we repeat at the bottom exactly the same categories we had and the same text as we have from the previous slide. And at the top here, we actually go into some detail. So it points out that we're really recording for each use case 2 types of information. The source of the parallelism, because as we'll discuss later in this class, parallelism is always, and we've actually already illustrated, parallelism is typically done by taking associated data, whether that data be the actual data of data or is the mesh points of simulations, chopping that data up into parts, so-called domain or data decomposition, and assigning each part of the data to a different core or a different node of your parallel machine. And here, the sources of parallelism is the people or households whose data has been gathered. And if you look at this, at actually other cases, you will find people enter in 2 ways. Here, because you're not allowed to look at the data, the people enter as the subjects whose data is gathered. In most other applications, they might enter both as the subjects whose data has been gathered and the viewers. Like if look to say Facebook, which actually isn't a use case, but could be, should be, or could be. Facebook, you see a lot of data from people, so you decompose that data, but also you have different people viewing it. So there you have both forms of parallelism. Parallelism in the original data and parallelism over the people using it. And the Facebook system has to support both parallelisms. And its back-end disk has the data of the people, and its front-end access must support major parallelism from all the smartphones or what have you accessing them. So the next thing, that parallelism is, as I said, always in purple. We also have in blue, the processing or computation class. And here we have three classes, which are actually typical classes of relatively straightforward, uncomplicated, traditional data sources. We have search and query, because typically you want to do what databases support very well. Do simple searches or relatively straightforward searches, often specified in SQL. And you want to well, SQL specifies the query, and you support that with indices. That's why we have the index category here, which enable those searches to run fast. If once we start using MapReduce and moving it to a more modern data processing architecture, the obvious use of MapReduce would be to take total queries and link and integrate the results of all those queries. That's the traditional actual use of map, because the reduction operation in MapReduce is one that integrates things together. In this case here, the integration is actually probably quite simple, because you're going to be looking at averages, the total worth of all population, of a population class of the people of a particular ethnic class or something like that. So these are global sums or global averages or correlations and things like that, which involve effectively a so-called reduction operation, where you take the results in each node, add them all together, and then take that final addition, and which is usually done over many different things, and presenting that to the person who asked for this action. So that's called MRStat for MapReduce or simple statistics. All right, so as I said, this is just we're on use case one. We've seen the use case, and we've seen the discussion for that use case of the parallelism source and the computation and processing class introduced for the first time in this use case. We will not tend to do that again, except maybe for some things like people, which have different aspects. We sometimes repeat some of the quantities. Here we have another application from the National Archives and Record Administration. It's sort of related. It's government data. It's a rather broader set of government data. So here I say the parallelism is over item. In general, I use the word item to represent the thing that is stored within the data. And here we have government items. Some of those government items are associated with people, some with government units, and so on. And so this needs to has the same type of processing as we saw before, MRStat, search and query indexing. It also adds PP, pleasingly parallel, because if you look at what the approach is, there's a whole set of things: physical and legal custody of the data, pre-processing the data for viruses, identifying formats, doing indices, categorizing the records as to their privacy status, transferring formats to different formats. And all of those, actually, except the indexing, are done independently. So that's why it's so-called pleasingly parallel. A bunch of operations which run on all of the items in the data set independently. And then, of course, we have to search and retrieve this data set to particular requests, both by sort of official users and public users. And here we have hundreds of terabytes of data. They're running on commercial databases with obviously a bunch of support software and specialized search products. And as this moves forward, you will find these use cases have typically three sections: application, current, approach, and futures. The futures of use case one don't exist for 75 years. In this case, we have a future in the near future, and here they're pointing out that there are a lot of distributed data sources, because every agency has its own data, and somehow they need to be logically centralized. And you probably don't want to make it actually centralized in the same place, because that's pretty inefficient, a lot of data transfer. Rather, you're likely to have a distributed storage with each agency maybe making different choices to the cloud they're using and so on. And so we need to federate the clouds and avoid actually transferring the data, but just leave it where it is and take logical custody of that information. So here we have some comments on the classification. I already pointed out the pleasingly parallel classification, which in a MapReduce framework is called the map-only example. And that's actually, it should miss out item 4. It should just be 1 through 3 and 5 in the current approach. And because item 4 was making the index, which is not pleasingly parallel. Some parts of it are, but the overall making of index has some global issues attached to it for obvious reasons. So it's actually typically not, it would not be called pleasingly parallel. However, taking each data set and making certain they are using a modern format is pleasingly parallel, because you do not need to integrate across the data sets. You just need to do the same thing for every item in the data. So here I just listed people, though they're actually similar to the use case 1 items. So here I said government items, and if we go on to the general discussion in the next unit, we will discuss very common items like images, health, electronic medical records, books, web pages, sequences, scientific observation, etc. And for this particular use case, items are government data. Here we do have parallelism actually with the people viewing the data. For use case 1, we don't, because of the 75-year rule. It's the only people viewing it certified government people allowed to do that. We don't have the public viewing. But for other data, almost all other data, anybody, with some restrictions, lots of people can view it. So here we have a couple of related use cases, one being the current example, and the next being some future example. And they each actually are using a new idea, namely the use of recommender engines, which is indicated at the bottom by collaborative filtering up here, which we'll discuss on the next slide. And the idea here is that surveys, as anybody who writes surveys knows, are very flaky, and that most people don't bother. We get so much email. When we get the sweet email saying, please spend 15 minutes telling me how you're doing, we know it will actually take 2 hours, and we never respond to the email, the survey request. Anyway, we don't gain anything. It's very rarely do you gain anything significant from answering a survey. So it's pretty hard to get people to respond to surveys. And so effectively, the idea here is to fill in the gaps using recommender systems. That's how Netflix and Amazon decide what you want. You don't fill in the survey saying what you want. They take a look at you, find out who you like, see what there's other people who've done in the world, and use that to suggest what your answer is. And so it's a rather interesting technique. And here they have around a petabyte of data. It's streamed, which is a characteristic that we will learn more about. But it's only streamed in a sort of specialized times, like while the census is happening. So we don't actually put it down as a streaming category. That's a little different from some of the other use cases where streaming is continuous. There's obviously important security constraints, confidentiality and secure, it says, and there has to be properly provenance, namely everything must be auditable to see that the right processes have been done, because that's what the law says. The data quality should be very high, bad data should be removed, and tests should be performed to look for accuracy and reliability. And they use actually a pretty interesting collection of modern technologies of Hadoop and Spark, which are traditional and iterative MapReduce, Hive, which is the SQL interface on top of NoSQL databases, R, which is a big statistics package, SAS, a commercial statistic package, Mahout, which is a machine learning library, I don't actually know what Allegrograph is. MySQL is a well-known database, as is Oracle. Storm is for streaming data. Big Memory is important in-memory technology to make cloud applications run faster. Cassandra is a NoSQL database, and Pig is a high-level piece of software built on top of MapReduce to allow you to code MapReduce applications faster. And so here they point out from the future is there is a lot of need for sophisticated analytics to be developed to improve survey responses by filling in the gaps. And then you have to find out how good all that stuff is. And so here we have our discussion of new ideas which were introduced there. And the one that I highlighted here is collaborative filtering, which is a key algorithm behind recommender systems, and they're used to estimate values of nearby points. And it's sort of a very generalized, sophisticated interpolation or extrapolation method, which is not it's not quite the same as traditional methods, because there's so much missing data in these types of applications. You can't use the traditional averaging techniques that which you learn about for interpolation in your elementary textbook. So here we are. We come to the variant of this, which is same basic idea actually of using collaborative filtering, but it involves new types of data, because the world is full of new types of data from the web, from smartphones and things like that. And so the opportunity, and then we can do web scrape data, electronic transactions, social media, geolocation, and we can get all that information, and we need to do the same types of things that we did before with the same type of software stack. So this is sophisticated new software to do surveys, where those surveys are going to probably be even more difficult to interpret because they're done using non-traditional data. And that particular use case introduced no new classification, so there was no follow-on slide for that. Thank you very much.